Welcome to today's webinar, Development of a Dedicated Hydrogen Combustion System for Heavy-Duty Application, brought to you by Convergent Science and IFP Energies nouvelles. Thank you for joining us today for the 10th installment of the 2024 CONVERGE webinar series. My name is Matthias Sulis and I am part of the business development team at Convergent Science. I will be your host for today's event. I'm glad I can be here with you today and hear from our partner at IFPEN about hydrogen combustion system and heavy-duty application. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, CONVERGE, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. CONVERGE features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our client. IFPEN is a major research and training player in the field of energy, transport, and the environment. From scientific concept with the framework of fundamental research through technological solution in the context of applied research, innovation is central to its activities hinged around four strategic directions: climate, environment and circular economy, renewable energy, sustainable mobility, responsible oil and gas. As a part of the public interest mission with which it has been tasked by the public authorities, IFPEN focus its effort on bringing solutions to the challenges facing society and industry in terms of energy and climate to support the ecological transition. An integral part of IFPEN, IFP School, its graduate engineering school, prepare future generation to take up these challenges. Since 2015, IFPEN has been collaborating with Convergent Science to develop the CONVERGE CFD software and utilize this platform for collaborative research with academic and industrial partners. By 2024, more than 20 PhD and postdoctoral students will have conducted their research using the CONVERGE CFD software. In the coming years, IFPEN plans to work with Convergent Science to extend the capabilities of CONVERGE CFD for simulating highly complex processes. Now it is time to introduce our two speakers for today's event, Vincent Giuffrida and Olivier Colin. Dr. Olivier Colin has 28 years experience in the R&D domain of turbulent combustion and pollutant modeling, PhD supervising and coordination of research projects. He was a student at École Centrale Paris in France and did his PhD under the supervision of Dr. Thierry Poisson on LES of gas turbine, taking part of the development of high-order finite element scheme for LES and to the thickened flame LES model. Since then, he is a research engineer at IFPEN in Rueil-Malmaison near Paris, a French research center dedicated to energy. He participated to the proposal writing of 3 European projects on LES, 3 French projects concerning LES in piston and gas turbine engine, and 2 early French program definition of RANS combustion and pollutant modeling for PSA and Renault. He has been project coordinator of the French ISMAPE and OFELIE project dedicated to soot and oxygenated fluid pollutant modeling for piston engine and gas turbine. He has been in charge of many research studies concerning turbulent combustion and pollutant modeling in both LES and RANS. He supervised or co-supervised 15 PhD theses since 2004. He published more than 30 articles in international journals with scientific peer reviewing. He is one of the main contributors to the development of ECFM 3Z, TKI, AKTIM, NORA, and ADF PCM models in RANS, and ECFM LES, ISSIM, TFM, and EDSIM in LES. He is a constant contributor of the CSI IFPEN collaboration since the beginning of 2015. Mr. Vincent Giuffrida got a master's degree specialized in energy option at SIE ENSMA in Poitiers, France. He joined IFPEN in 2018 as a combustion engineer for the CFD team. He worked for 6 years with IFPEN on gasoline and diesel engine technology and is currently working on hydrogen internal combustion engine. Without any further delay, I will now pass the ball to our speakers. Thank you all.
Okay. So thank you, Matthias. So now I present the development that we have done on this dedicated hydrogen combustion system for heavy-duty application. So for this CONVERGE webinar hydrogen. So with my colleague Olivier, Colin, and also some information on Shui Liu. Yes. So, okay, let's have a look first on the overview of this presentation. So I'll present first a little bit of context of hydrogen internal combustion engine for heavy-duty application. In the second part, Olivier and me will present a little bit the combustion ECFM model development and its usage inside CONVERGE. In the third part, I will present here specifically the development of the combustion system by CFD and comparison to experiments. Finally, in the fourth part, I will detail a little bit on the ongoing research program on H2 internal combustion engine physics and technologies. And finally, I will do some key takeaways and also perspectives. So first, let's start with the context of hydrogen ICE for heavy-duty application. The question is why hydrogen ICEs for heavy-duty application? So in fact, as you can see here on the right-hand side of the slide, you have here the description of the CO2 emission regulation of the European Union function of the year. Here you have, for example, here 2025, which is the year where we are. So you can see here that the regulation for the European Union is minus 15% in 2025, and we are going to have a revised standards that is more strengthened with a minus 43% CO2 emissions compared to the original standards that was a minus 30%. So in fact, hydrogen has a place to reduce this emission, and that's why it could be a good solution for heavy-duty application. Second thing is the fact that it's considered as a free carbon technology now. In fact, in the previous regulation, the hydrogen, the threshold for zero emission vehicle was a 1 gram per kilowatts. Now it has a little bit changed. For example, you have for trucks 3 grams CO2 per ton transported per kilometer, and for buses and coaches, 1 gram CO2 per passenger transported per kilometer. So in a way, it has been softened, and now hydrogen combustion system are able to match this regulation. And last but not least, hydrogen combustion system is based on existing technology because we have a lot of things on gasoline and diesel technologies, and also infrastructures. So it's a cost-effective solution if you compare to fuel cells, where we have some rare materials like platinum. So a quite good solution in terms of, it's a cost-effective solution. And also it's a technology that is dedicated to high power application when, for example, BEVs in fact does not meet the specification for requirement because of the mass of batteries that is very high for heavy duty application. So for example, for heavy duty, some light duty vehicles, off-road, and also motorsport. And H2IC was identified, in fact, as a possible solution for heavy duty application at IFPEN. Concerning the development studies that we realized at IFPEN and the activities on this subject, so IFPEN is providing, in fact, support for the development of hydrogen engines through several partnerships that I will present after an example, and by using appropriated, in fact, dedicated means. This dedicated means, for example, CONVERGE. Here you have some example with a light-duty engine vehicle where we have recalibrated the simulation to the experimental results. We can obtain also results on the 3D side here with CONVERGE. So it's a good tool for us to design combustion system, assisting with CONVERGE, so with 3D simulation tools that has been developed in a way we will see it after at IFPEN with the combustion model. The second thing we have is hydrogen test cell, in fact, to validate our simulation. So we have 4 hydrogen engine test cells at IFPEN in Solèze premises, so in Lyon, in France. And we are able also to run some engine here. Now, concerning the partnership, we have, for example, I will give one example here. So it's the consortium example, which is a direct retrofitting of an MD8, in fact, a diesel engine, into a nitrogen engine, the MH8 ICE, with in fact port fuel injection and water injection with a reduced compression ratio. As you can see here, it has been put it inside a real truck, in fact, and you have, in fact, a lot of people that have been involved. In fact, Renault Trucks, for example, ADEM, the laboratory Prism also, IFP Energies nouvelles, and Plasticomium. So this kind of engine is a specific way to do. In fact, just retrofit from existing technology towards hydrogen, direct retrofitting. We replaced, in fact, the diesel injector by a spark plug and the Praetor by a nitrogen injector, in fact. But here, the focus will be on another way to create hydrogen engine, let's say, which is a dedicated combustion system that have been developed here at IFPEN with specific aerodynamic constraints, which is a kind of tumble motion, and also direct injection to improve the performances compared to this one. And finally, concerning the introduction, at IFPEN, we are using kind of V-diagram to design combustion system. As you can see here, it's our workflow. It begins from, in fact, a pre-design by simulation and advanced optical diagnostic tools to a final design, in fact, using 0D and 3D simulation tools in CONVERGE. We use also afterwards single cylinder engine manufacturing and design. We do some tests on the test bench on a single cylinder engines at the moment. Then we can realize some understanding by 3D CFD of the result that we obtain in the single cylinder engine experimental test. And then we can afterwards, for some application, realize a multi-cylinder design on manufacturing and even implement it on demo trucks. Here, I will only focus on the things that interest us. In fact, the CONVERGE, how we develop the combustion system with CONVERGE. So it will be only on this part. So in fact, the final design, how we optimize the system, and the understanding by 3D CFD of the results that we have obtained on test bench. Okay, so now I will switch on the model that we use for this development. So it's a ECFM model development and the usage, how we run the simulation and how we set up the simulation with that. So I let maybe Olivier for this slide.
So here we use obviously CONVERGE for CFD modeling. And the RANS approach also, it can be used with LES. In this simulation, we use the combustion models developed at IFPEN and implemented in CONVERGE with CSI. So the first model is ISIM for impulse stretch ignition model. It's a spark ignition model that provides a flame surface at spark timing. And this flame surface is given to the ECFM combustion model. So this is the extended Coherent Flame Model, which accounts for flame turbulence interaction at the subgrid scale. So here you have a schematic view of the turbulent flame, and this flame is described thanks to a flame surface density equation, where basically the flame surface density is the ratio of the flame surface per unit volume. Today, I'm going to speak a little bit about the last developments we've done in ECFM concerning the turbulent stretch model. And finally, we also use the TKI model for auto-ignition occurrence, that is for pre-ignition and knock. TKI is for tabulated kinetics of ignition, and it accounts for the auto-ignition delay and the heat release rate through lookup tables. I forgot to say that for the reaction rate, it's simply the multiplication of the flame surface times the laminar flame speed, and this laminar flame speed is also tabulated like with TKI, using a mechanism that is prescribed by the user, and there is a pre-computation of this table before the CFD computation. So if we make a focus on the flame surface density equation and the improvement we've brought, here I present the flame surface density equation and the two major terms in the turbulent regimes are the turbulent strain term, AT, and the curvature term, kappa SD. And this turbulent strain term can be decomposed into a mean contribution and an SGS contribution. And this SGS contribution is the most important one in turbulent flows. Today in CONVERGE, we have different models available for the Flame regime, the ECFM model, the Charlotte model, the Bogreen model. But we observe that these models become quite inaccurate when going to H2 and especially for the lean mixtures and high turbulence intensities. This is why we worked on developing a new expression, which is called LPF for low pass filter. And this model was developed at IFPEN for both the flamelet and the TRZ regime. And the final expression of the model is actually quite simple. It's given here. So we developed and we made a comparison of this model with DNS. So first of all, it was done with DNS of isooctane and then DNS of H2 air flames, lean flames. So for the isooctanes, the lowest number is larger than unity. You have here the results at 3 Karlovitz numbers. So case A here is in the flamelet regime. Case B and C are in the TRZ regime with much larger Karlovitz numbers of 20 and approximately 50. The DNS is in red, black cycles. Bogreen, Charlotte are shown also, and LPF model is in red. And you can see that the agreement of LPF remains good also at large Karlovitz numbers, unlike with Bogreen and Charlotte models. We also further improve this model by making a normalization in LPF, which corresponds to the label here IMP in red, in green. And you can see that the results with the normalized LPF version are even better than with the original version. And finally, we made a comparison for lean H2 air mixture. And here you can see that with the last normalized version, we got a very good agreement in terms of turbulent strain, even at the largest Karlovitz number. So this model is today available in CONVERGE 3.1, and it's given by ITNFS flag of 8. The second point I wanted to address is about the generalized fuel formulation for ECFM, because in previous ECFM implementation in CONVERGE, we were limited to fuel components of the form C, X, H, Y, O, Z, where X needed to be strictly positive, which means we could not perform H2 combustion. Today with CSI, we have developed a new formulation where all fuel components can be of the form C, X, H, Y, O, Z, and M, with arbitrary values of the coefficient X, Y, Z, M, which means that today we can use CO, H2, and H3 as possible fuels. So just to explain the different species, because there are a lot of them, I'm going to summarize now which species corresponds to what. So in the unburned gas, you have the unburned fuels, which are given by UF underscore and the name of the fuel. And if you use H2 or CO as a fuel, you need to name it differently. That's the only thing you need to be aware of. So for instance, for H2, it needs to be UF underscore H2 fuel, for instance, or UF underscore CO fuel. And then you've got the 6 other species in the unburned gas, CO, CO2, H2, and 2H2O. If you use H2 as a fuel, of course, H2 is going to be set to 0. These unburned gases are then oxidized and also transferred to the burned gases. So in the burned gases, the fuel become F1, F2 without the UF. And H2 fuel is present but is equal to 0, and CO fuel is also equal to 0. Actually, all the H2 and CO are contained in species CO and H2. And otherwise, you have CO2 and 2H2. And then you have additional species. So if you use the post-flame model 0, you have chemical equilibrium of OH, H, and N. And if you use the post-flame model 2, you can use SAGE in the burn gases with any complex chemistry mechanism, and then you have NMEC species in the burn gases. And the naming in the unmixed fuel is very similar with the UMF prefix, and in the unmixed air you have unmixed as a prefix. Concerning the fuel oxidation paths, so they are similar to what they were, just that they are now generalized for including the N atoms. So for fuel oxidation by premix flare or auto-ignition, we do like before, we define a mean fuel CXHY-OZNM just as an average of all the fuel fraction you have in the unburned gases. And then this mean fuel is oxidized by two simplified reactions, which give CO and CO2, and the N atom is transformed into N2 simply. And in the case of rich condition, the unburned fuel becomes is transferred to burnt fuel. Now, for the post-oxidation in burnt gases, as in previous version, you've got, as I said, option 0, where you have a two-step fuel conversion in CO and CO2 if you have a C-containing fuel, plus equilibrium. Option 1 is equilibrium calculation for all species, and option 2 is a user-defined chemical mechanism solved by SAGE. So I'm going to let Vincent present the following slides.
Okay. So thank you, Olivier. So now to present a little bit what we have done with this stretching model, in fact. We have tested this LPF turbulent strain model on, in fact, a nitrogen fuel air equivalence variation, where we had, in fact, experimental results. So as you can see here, it's on a turbocharged light-duty engine. So we have tested blue-green and LPF turbulent strain model on a light-duty hydrogen engine, displacement of let's say 500 cubic centimeter. The operating point with hydrogen was a 3000 RPM 10 bar IMEP with a fuel air equivalence ratio variation from 0.3 to 1. The combustion has been calibrated for all these points on experimental result using the parameter alpha ECFM. And the key in it is, in fact, a modeling constant for the ISIM part, in fact, the ISSIM model for the ignition for initial flame blinking is set at 3 for all cases. In fact, we have kept the same constant for this parameter. Then you can see here the variation that we have obtained for blue-green and for LPF. What you can see is that for blue-green, we have a large variation, as you can see here, alpha ECFM function of fuel air equivalence ratio, a large variation of the constant with fuel air equivalence ratio that is from 1.8 for low fuel air equivalence ratio to less than 0.1 for high fuel air equivalence ratio, which is quite difficult then to calibrate for instance, when we have experimental results. If we look at LPF, it's a much reduced variation, like you can see here, alpha ECFM function of fuel air equivalence ratio. We have a variation, but it's quite small, and the only remaining variation are mostly linked to the increase, in fact, here at low fuel air equivalence ratio of thermodiffusive effects, low Lewis number below 1 for hydrogen, and also the switch at higher fuel equivalence ratio, from flamelet to TRZ regime when FRR decreases. So from 1 down to 0.3. And it is not accounted for the moment in present in ECFM model. But we can see that LPF is better in terms of variation of this parameter compared to green. So now I present a little bit how we can set up multi-fuel ECFM setup, engine setup. So here it's an example of the CONVERGE Studio settings that have been used to set up, for example, correctly multi-fuel ECFM case with, in fact, hydrogen and CH4 mixture. So on the left-hand side, you can see here the tab for the combustion modeling settings. So in general, you here put the fuel species name. So you have methane and hydrogen. as Olivier said, we needed to change. In fact, we must set this fuel species name different as H2 because H2 is a product, in fact, and not a reactant. So it must be set different. So we called it here hydrogen, but we can use H2 fuel or whatever you want, as long as you know what it is. So hydrogen, and in terms of polynomial, so NASA, so thermodynamic, you need to set hydrogen the same, in fact, as H2. So you just need to copy the NASA polynomial of H2 to hydrogen. That's all. Then if we look at the model tab, so here for ECFM or an ECFM 3Z, so here you will say that you want an ECFM setup. And in general, you will have all the constant parameters of the model. So the alpha ECFM that I told just before, 1. So here you can see it here. So it was 0.08, for example. So it's a constant for turbulent stretch. You have also a constant that we don't use here at IFPEN, which is a constant for the surface density destruction term, in fact. Things you have also to do is to realize an automatic reinitialization, which means that from cycle to cycle, you need to switch from burn fuel to unburned fuel, because otherwise you will not have combustion. So you need to do that, and the simplest way to do that is to do an automatic reinitialization as it is set here. You have also to create, that's important first, in fact, that's the first things to do, is to create the species we need, so the unburned species, unburned fuel species, and the unmixed species. So by clicking this button, you will add, in fact, all the unburned species, UO2, UN2, etc., that Olivier described just before, and that will enable you to realize the simulation then, and to run the simulation. Then you have also the post-flame model. Here, for example, we can use Sage. In fact, by activating this, you will in fact resolve the chemical only in the burnt gas zone, and you can use, in fact, a specific NOx mechanism to know what is the amount of NOx present on the burnt gases. So it's more detailed compared to the simplest Zeldovich mechanism. We will see this just after, because we have done some tests on this aspect. And finally, you have also, as I've described, Olivier, the turbulent flame stretch model, which is the one you described with ETNFS, SUIO model, or LPF model. That's here that you will put, for example, Bouguin or LPF with the number that he said, so 8 for LPF, and that seems to be better adapted for hydrogen. Okay, so now that we have described a little bit how we set up this thing, we can also do some main post-processing variables that are a little bit different if you compare to Sage. We're able to do much more things with ECFM. As you can see here, we have, for example, the output of ProgVar, that is the global progress variable for the combustion. You have also for the progress variable for propagation mode and for auto-ignition mode. This enables you, in fact, to look at the spot where you could have auto-ignition. For example, here, I just have done, in fact, a 3D post-processing with the flame that you can see here. It's an isosurface of the flame, so C equal to 0.5, so 50% of the mass burnt, of the fuel mass burnt. So it's a flame, in fact. And you will have here, and it's colorized, in fact, by the C auto-ignition, which corresponds to the kind of auto-ignition inside the engine. So the lighter it is, it's where, in fact, you have auto-ignition spot. So that enables you to see where you have auto-ignition points and to, for example, improve your engine design, etc. Another things you can do is to use omega CFM or omega TK, in fact, to look at the fuel reaction rate in propagation mode and auto-ignition mode also. And you have the possibility, in fact, to calculate the percentage of mass that is burnt, in fact, in auto-ignition mode. And so to know where you will have knock, in fact, compared to Sage, where it's only, with a pressure curve, for example. Here you have specifically something that enables you to calculate this percentage and to see where you will have chance to have knock. Okay, so now that we have described a lot the model, I will now switch on the development that we have realized on the combustion system by CFD and the comparison to the experimental results. I will first describe a little bit the engine, hydrogen engine. So it's an in-house 2.1 liter single cylinder direct injection heavy duty engine that has been designed by CFD alone. Here you have the little description, so you can see here the intake ports, exhaust port. You have the injector here placed in at the middle, let's say, of the intake ports, between the intake ports. You have the spark plug here at the center of the chamber. The displacement is 2.1 liter, as I said. Compression ratio around 12. The injection system is the FINIA one, CAG 15, so 15 grams per second at steady state, so flow rate, at a maximum pressure, injection pressure of 40 bar. Then, so this engine has been manufactured, and the experiments has been realized at IFPEN Lyon premises in France, identical to the optimal CFD design. So let's have a look at how we decided to optimize the system. So different topics, in fact, were addressed with CFD concerning the architecture and the targeting, which one to choose, in fact, to have the better mixing and the better combustion. In fact, first we decided to optimize or to see what was the best engine architecture for mixing. That's what you can see here. In fact, you have, for example, here on the left-hand side on the graph, the TKI. And you can see that using a kind of tumble, it's a swamble concept. It's something that we have developed here at EFPEN, that is a mix between swirl and tumble that enables you to have more turbulence. You can see that you can reach higher level of turbulence. Here, function of the concurrent degree. At top densitor, that is 720, we have, let's say, 100% more turbulence compared to the swirl-based design. If we look now at the standard deviation of the fuel air equivalence ratio, which corresponds basically to the mixing, in fact, to the velocity of mixing, you can see that at top dead center we have a more homogeneous mixture, so a lower standard deviation on fuel air equivalence ratio, which means that here you can see here also on the 3D visualization, you have the fuel air equivalence ratio on two cut planes of the combustion chamber. If we compare the swirl on the swamble concept, clearly you can see that we have a better mixing with the swamble concept. It means that architecture with high turbulence level is clearly beneficial for mixing and for hydrogen combustion system. So the chosen one was the swamble one for this architecture. We have also the impact, in fact, of, we have studied the impact of H2 jet targeting on the mixing. So you can see here also the same, so the TKU level, because in fact, hydrogen has a lot of momentum because it's a supersonic jet. We are able, by doing an equation between the hydrogen jet and the internal motion, tumble motion, kind of, to generate more turbulence, as you can see here. More tumble first, in fact, because it's a tumble that generates turbulence. So first, more tumble, as you can see here on the right-hand side, if you compare the base targeting of the optimized one, and then more turbulence, as you can see here. And in the end, having more turbulence enables you to have more mixing, as you can see on the 3D visualization here. If we compare to the base targeting, here on the optimized one, we have quasi-homogeneous mixture. So the equation between internal aerodynamics and H2 jet is crucial for mixing. And finally, we have validated this CFD with respect to the experimental results, doing in fact the feedback from the experimental result to 3D CFD to the experimental results. We have here a comparison between experimental results and simulation. You can see that we have a good matching on the in-cylinder pressure and also the apparent heat release rate. Here we have also the flame propagation. You can see more of the intake side because we have more turbulence on this side. So current trends were observed in simulation, showing the validity of the CFD tool to design, in fact, the system. That was the key point. So the first two topics are more detailed in the presented paper SCA 2022, and if you want, you can have a look on this paper for more information. After that, we have decided to realize a variation, spark advance variation of an operating point, this one, so 1,200 RPM, 9 bar MEP, with a start of injection of 260 conjugal D3 before top dead center at lambda 2.5. We have realized the spark advance sweep from 0 to 14 CAD and was performed for feedback, in fact. And after an alpha ECFM calibration at optimal spark advance, that's all. We just calibrate the alpha ECFM on this point. We obtain, in terms of pressure and BMA duration, these results. So you can see that we have good matching in the whole spectra, let's say, of the spark advance variation. Only for late spark advance, where you can see that we are not matching well, but it's linked also to the fact that we needed to have more injected mass to keep the same IMEP, which was not possible for us due to consuming time of the simulation. So yes, that's the only point. Otherwise, we have a good matching. So good accordance within the whole range of spark advance sweep. And also the fact that we have the same indicated efficiency of 47% if we compare to experiments with simulation. Now for NOx emission, we have also compared the experimental result to the result of simulation. So here you have the result obtained experimentally with the variation of spark advance. So when you have earlier spark advance, we have more NOx, it's normal. You have more in cylinder pressure and more temperature. And if we compare with the simulation done by Zeldovich, so no post-flame model, only the thermal one, you can see that we are quite far from the result of the experimental results. We have a factor 2 or 2.5 for some points. If we use the post-flame model too, so SAGE, in fact, is the Berg gases with a Klippenstein mechanism that is described here, reference here, you can see that we are able to match better the experimental results. So yes, so in absolute, we are able to reduce this difference, which means that, in fact, there is not only thermal NOx with hydrogen, but there is also non-thermal NOx. And this mechanism is able to get that. Okay, now I'll describe just a little bit the result that we have obtained with this engine. So based on the proposed CFD design, so we have realized the experimental tech campaign on a full map, full engine map, as you can see here, from 900 RPM to 1900 RPM, and from 4 bar IMEP to 22, 23 bar IMEP. And you can see that we obtain quite good results. In fact, we are able to obtain maximum indicated efficiency of 48% on the core of the engine map. The result was obtained with a specific model of double-stage turbocharger architecture for this kind of application, with a lambda, in fact, that was ranging from 1.8 to 3. In line, in fact, with previous CFD results, as you can see here, the 1200 RPM 9 bar map, we catch, in fact, the 47% indicated efficiency, as we have found just before. Okay, so you can see that we are able now to kind of model and describe the engine and to have good results and to design combustion system for hydrogen combustion system. But there are also some remaining challenges for H2 combustion, and there are 3 for us. We are studying here at IFPEN 3 main topics that remain challenging for H2AC modeling. First, the hydrogen injection and mixing. In fact, as you can see here, using RONS or LES, you don't have the same results, which means that the RONS and LES mixture are quite different, and the supersonic hydrogen jet have associated vortices that are difficult, in fact, to model with RONS. It's what we think, in fact, and that's why LES seems to better, in fact, diffuse the hydrogen compared to the RONS one. So significant differences are observed between RONS, LES, and real mixing, and we have work to do on this subject. The second subject is the H2 combustion and wall heat transfer. As you can see here, we have done some 1D DNS to see a little bit what are the difference with methane. You can see that there is a lot of difference if you compare, for instance, with hydrogen at different richness. And also the flame propagation, because the Lewis is below 1, you have thermodiffusive effect that affects the flame wrinkling, and you can see that hydrogen have much more wrinkling compared to to methane flame. So okay, that's what I said here, and also the whole heat transfer, but that's different compared to conventional fuel, methane. And last but not least, there is something that is important with hydrogen engine, is the preignition and knock with H2 that is more important compared to conventional fuels like methane, linked in fact to local hotspot, hot residual gases, carbonaceous deposit, all these things we don't know exactly because it's a stochastic event. You can see here on different cycles that we can obtain knock, not knock, we can obtain early spark that will lead to very high in cylinder pressure. And we are not able, in fact, to have, it's a stochastic event, in fact. So it's something that we need to investigate, and that's what we are investigating now. So preignition and knock. And all these three challenges, as I said, are addressed at IFPEN with an ongoing specific research program associated. And I represent now, in fact, this ongoing research program. First, as I said, the hydrogen air mixing. So we are using, in fact, experiments to measure, in fact, the mixture between hydrogen and air. This method is called the inverse Pelif method. And it's done in an HPHT vessel. In fact, we inject inside the vessel, and we see, in fact, the diffusion of the jet using this fluorescence method to get, in fact, the mixture. In fact, as you can see here, it's the mass fraction of H2 inside the cell. And we compare it to Ron's calculation, for example. Here you see the same, in fact, the fact that Ron's calculation is less diffusive compared to average experimental results. So yes, so it's something that we use. The other thing that we use is the Schlieren visualization. You can see that here there is not so much problem. We are able to match the penetration quite well. For example, here for Finia CHG10 injector. So yes, so the first interesting results observed are the fact that H2 round jet shows too low diffusion in air, and H2 LES here, as you can see here on the axial line, show better, represent better the diffusion. As you can see here on the right-hand side, here on the graph, we have compared experimental results, Ron's result and the LES on one only shot, and you can see that in fact we are able to better match the diffusion with the LES compared to Ron's. Some works to do on the Ron side and on the Ron side to have better description of the mixing. Concerning the transfer, we are also working on that. As I said before, we have studied in 1D DNS the flame wall interaction between CH4 and H2. You can see that the quenching distance is quite low at stoichiometric condition for hydrogen compared to methane. But at lambda 2, hydrogen reach almost the same quenching if we compare to methane. And in the end, we have a lot of difference in terms of dimensionless heat flux if we compare methane and hydrogen. Yes, so that's what I said almost. And hydrogen quenching distance that increase with dilution is what we see here. To study that more in detail, we will use a future experimental program studying HPHT vessel environment. We will measure, in fact, wall heat fluxes here on a slide that it's a specific geometry to generate tumble, and to get then by using thermocouple wall heat transfer on this slide here. We will use also inverse Pelif technique to measure also the mass fraction at ignition, H2 mass fraction at ignition, to be sure that we have the same mixture if we compare with experiment, and visualization also of the flame formed by Schlieren. Here you have a little simulation where you can see the mixing and the flame propagation inside the vessel. It's what we study now. Finally, on my aspect, so we are studying also preignition. As you can see here, we are using endoscope inside a light duty engine to try to see a little bit where are the spots where we can have, in fact, preignition and knock with an intensified camera. So it's done at IFPEN in Solèze. Here you have a visualization of the flame, in fact, the real flame inside the engine, experimental one, with the spark that you can see here with the very light one here. So it's, in fact, preignition is a major concern for H2 engine for efficiency, full load capacity, and also durability. So that's why the objective is to understand the origin of preignition, to see what is the flame propagation, and also to locate where are the spot of preignition, and to try to manage it, to remove this spot and to avoid preignition. I will let maybe Olivier present this slide. It's more on the modeling aspect.
Maybe you. Okay, thank you. You can keep the slide. So, okay, so we are currently working on 2 approaches. We are still working on ECFM. The first step we'll take is to account for preferential diffusion on the consumption speed at the resolve scale. That is introducing the stretch factor I0 in the equation shown here. I0 is today equal to 1, and when you have Lewis inferred to unity, like for H2 mixtures, I0 can be larger than 1. So the first thing is to include this effect at the resolve level. And then the most difficult part is to account for this preferential diffusion at the SGS level, and also to account for the high Karlovitz or the TRZ regime. And this is ongoing research in what we call ECFM HK for high Karlovitz. But we are also developing at the same time the thickened flame model, TFM, because it is a possible alternative to ECFM for SI engines. We have recently observed that the answer of TFM to stretch is altered by thickening. And so TFM in presence of preferential diffusion doesn't answer correctly. This is why we proposed a correction recently, which was presented last year at the European Combustion meeting, and that we will publish soon. And then the second challenge is exactly like with ECFM, is to account for preferential diffusion and TRZ regime at the SGS level. And for this, we rely on the same analysis that we use for ECFM using DNS, essentially of lean H2 air mixtures. Okay, I think that's all for the development part.
Okay, so now I will switch on the key takeaways on perspective of this study. So first, we can say that we have a dedicated heavy-duty engine at IFPEN, 2.1 liter single-cylinder engine that has been developed entirely at IFPEN. The whole process of design and optimization has been realized through CFD with CONVERGE, showing that we need high turbulence level that is required, in fact, for H2 air mixing. So that's why tumble motion is preferred for the moment for this kind of application. We saw also that the specific targeting of the injector enables further improvement for mixing and also turbulence, and so for the combustion also. We have seen also that and observed a good efficiency, indicated efficiency of 47% that was predicted by CFD and confirmed experimentally with even 48% for other points, other operating points. The experimental results show further modeling improvements that are required for mixing abnormal combustion in transfer validation, also the combustion itself. So a lot of work needs to be done, but IFPEN is actively working on this subject to improve CFD modeling of H2 combustion with CONVERGE through different research programs that include advanced experimental tools that I have described just before. And just to finish, I would like to thank all my colleagues that work on this subject, so CFD team, development team, Olivier, etc. And thanks to all our partners, so Tenneco, first for providing the spark plug, Finia for providing, in fact, the injection system, and finally Danielson Engineering for manufacturing the engine. So thank to all of them, and thank you for your attention.